Welcome to Math 1324, Lecture 5.3. Today we're going to continue our study of finances. We're going to look at something called annuities. We're going to look at future value in a special way. And we're also going to look at another concept that's very common in business called sinking funds. So our brief pause today is around habits. And our first quote says, "Your habits will determine your future." And we've been talking a lot about money in this chapter 5, both from the brief pauses, but certainly from the content. And it's really been my intention to kind of give you a wake-up call around financial knowledge. The wake-up call that I didn't have, or I didn't take, I should say. I'm sure the knowledge was available to me, I just didn't realize it and didn't pursue it. I believe I've already said in these lectures that had I learned and adopted, learning is one thing, but adopting is another, and that's why we're talking about habits today. It's one thing to know something, but unless you put it into practice, things aren't going to change. And I'm not exaggerating when I say this next statement. Had I known and adopted even just some basic of these financial strategies, I believe I'd be anywhere from $250,000 to $500,000 richer. And a lot of that has to do with the home loans I've had and the length of periods of mortgage, excuse me, and also a focus on a monthly payment as opposed to the time value of money. So not only did I have mortgages, but I refinanced and took more money out. In my mind, I was getting cash, but really what I was doing was creating a burden for myself. I was robbing my future by giving myself cash today that I had to pay back. So I really want to encourage you to think through what we're learning here. Think through what your habits are, not only in relation to money, but maybe even in relation to your schooling, your academics, your health, etc. And it doesn't take big steps, it takes little steps that you do consistency. So the first quote is, "Your habits will determine your future," and I don't think there's anything more true than that. Americans are extremely obese compared to the rest of the world, and yet if we walked just an hour a day, maybe even half of that, most of us would be in pretty good shape. Depending on what they are, our habits will either make us or break us. We become what we repeatedly do. I don't think there's anything to be said about that except it's true. So what are the habits that you have? What are the good habits that you want to strengthen? What are the bad habits that you want to change and replace with something else? We first make our habits, and then our habits make us. And this can be true if whether they're good habits or bad habits. When I think about we make our habits, of course we make all our habits, but if you're much more intentional about your habits and the things that you want to bring into your life, then I think you're going to have much more success. There is no elevator to success. You have to take the stairs. Great quote, Zig Ziglar. Of course, there are a few elevators, but they run, very infrequently, and you have to be a really lucky sucker to get on one of those. Of the one winning lotto ticket, there were 200, 400 million that were not lucky. Okay, so you can hope for an elevator, but you may be at the bottom floor for a hell of a long time, and possibly even forever if that's what you're waiting for. You will never change your life until you change something you do daily. Again, I think this is very powerful about what we do consistently and repeatedly. Consistently and repeatedly. Those are your habits. If you want to be healthy, you need to move and you need to be conscious of your eating. If you want to be financially healthy, You've got to keep an eye on long-term investments and your spending. And then have the knowledge that banks and salespeople are not trying to help you. They are trying to make money for that organization. And there's nothing wrong with that, but they take advantage of our ignorance. And I speak to that again from my own personal experience. All right. Continuing on with our take-home portion of the test, what you should be up to now is to work on part 4. This is the one around buying a home. And what I've done here is I want you to see the difference between buying a home and having a home loan for 15 years, 20 years, and 30 years. I want this to be relevant to you. So a big part about moving away from the emotional side of purchases, and a home purchase, just like a car, is hugely emotional, right? You know, especially now with shows and stations like HGTV. You know, we want the crib, we want the flash crib, etc. So you got to be really careful. And so one of the things that you can do when you're figuring out how much money, you know, if you're paying it back in 15 years, the bank is not going to offer you as large a loan as if you're paying it back in 30 years. But you're also paying probably double the interest because of the longer time, if not triple. So, you know, one of the things to think about is your age. So when you're thinking about buying a home, project the age you will be in 15 years and imagine your home is paid off then. Really imagine it. Stop for a second and imagine yourself at whatever age that is and think, damn, my house is paid off. Our biggest expense is no longer there. And if you're, let's say 25, then at 40, you no longer have a house payment. And then do the same thing for 20 years. Okay, now I'm 45, not so much a big difference, but do it at 30 years. Holy crap, I don't want to be paying for my house until I'm 55 or whatever. Okay, so that's one of the big takeaways from this. Being mindful of really what you can afford that will make you happy. And remember that it's not necessarily your home that will make you happy. You know, it could be the fact that you're saving a boatload of money and you live in a decent neighborhood with good schools, maybe not the flash neighborhood, etc., that you could have afforded if you did a 30-year mortgage, etc. So this is very personal to you. You'll get to use your calculator. All the calculations are detailed out there. You're going to use the TVM solver. This is based upon assuming that you're in college now, that you buy a house 2 years after you graduate. So it's projecting, you know, when you'll graduate. It's asking you to figure out what the starting salary is for the job that you think you're going to get. And if you don't have one of those, it's telling you to use $50,000 because that's the average starting salary for someone with a bachelor's degree. So try this. I think it's, you know, I hope this is helpful and interesting. And I will say that I had a student about 5 years after taking my class called me and said, you know, him and his wife were just about to buy a house and he just couldn't remember everything, but he knew that 30-year mortgages, he needed to be really careful before they did that, and he couldn't explain it to his wife, and so they asked me to talk to them. So that was kind of neat. All right, let's get on with our lecture. Let's start with annuities. So far in this chapter, only lump sum deposits and payments have been discussed. You know, that you put a $10,000 into an investment and you earn interest, or you know, you borrow $20,000 and pay it back. Those are lump sums. Many financial situations, however, involve a sequence of payments at regular intervals, such as weekly deposits in a savings account or monthly payments on a mortgage or car loan. Such periodic payments are the subject of this section and the next. An annuity is a series of equal cash flows equally distributed over time. So a monthly payment that is the same amount, a payment twice a year that is the same amount. I pay for life insurance once a year. Even though I only pay it once a year, it's the same amount every year for 20 years. That is an annuity. So it's just the same amount of money, same period of time that you pay it or receive it. Okay. When you retire, you'll get a pension check. It really should be the same amount, and it'll be the same amount every month. So that would be an annuity coming to you. Examples of annuities abound. Mortgage payments, your paycheck, if you're salaried, being the same amount is an annuity. If you have a car loan, the payments are an annuity. If you have a car lease, that's an annuity payment you make. Rent payments are annuities. Insurance payouts, often insurance companies or courts will decide that the insurance must pay you so much a year or so much a month, and so on. Equal amount of money over the same period of time. If you are paying or receiving the same amount of money every month or week or year or whatever time frame, then you have an annuity. A regular annuity or ordinary annuity is an annuity where the first payment is made at the end of the period. Regular or ordinary annuities, the payment is made at the end of the period. Okay? A payment period is the time between payments. Maybe it's monthly, maybe it's weekly, maybe it's annually. The term is the time from the beginning of the first period to the end of the last. And your future value is the final amount or sum of all payments and interest. Okay? So think about this. If you are making payments, let's say you have a car loan and you're making payments, your future value is actually going to be 0 because you are paying down your loan until it is paid off. And so the future value of a loan is 0 because it's paid off. If you're putting money into an investment or a pension account, your future value is going to be a larger amount, and you're starting at 0, etc. Okay, so depending upon whether you're paying or receiving, the future value could be large or 0. So let's look at some examples. $1,500 is deposited at the end of each year for the next 6 years in an account paying 8% compounded annually. Find the future value of this annuity. So I want to kind of show you how this works conceptually. So we're paying $1,500 a year. And if you've gone to the TVM Calcs website that I recommend in the take-home assignment, you've probably seen something like this. And these charts can kind of help you visualize what's happening in a problem. And I will tell you that students are very confident about this test, Chapter 5 test, because they use the TVM solver. But the setup of these problems is not always easy. It can be quite confusing. So pay attention to the homework, do lots of problems, and make sure you got it. And definitely do that tutorial in the TVM Calcs in the from the first page of the take-home assignment. So we're making the payments at the end of each year. So at the end of year 1, we make $1,500. At the end of year 2, we make another $1,500. 3, 4, 5, and then at the end of year 6. Okay? So really, each of these payments is making its own interest over that period of time. This first payment, you don't get any interest the first year because you don't actually put any money in there until the end of that first year. Okay, but this $1,500 is going to earn interest for 1, 2, 3, 4, 5 years. Okay, the second payment is going to earn interest for 1, 2, 3, 4. The third payment, 1, 2, 3. The fourth payment, 1, 2. The fifth payment, 1. And our last payment, which is really kind of weird, but our last payment makes no interest because it's kind of like we're putting money in on the day we take money out. So it's a confusing example a little bit conceptually. So this is just for the first payment. Okay? So the first payment in year 1, we don't get any interest. But at the end of year 2, we get that 8% interest. All right? So at the end of year 3, we have the amount of money in our account from year 2 times the 8% interest, which gives us our total amount that we have now, the original amount plus all the interest. In year 4, it's the amount that we have in our account at year 3 times the interest, and so on and so forth. So the total amount that this payment is worth you can see is the $1,500 times 1.08 to the fifth power, which is 1, 2, 3, 4, 5. The number, the exponent, is the number of years that we're earning interest on that because it's being compounded each year. Okay? So let's go ahead. So if we think about that, the first payment is going to make $1,500 times 1.08 to the fifth power. The second payment, because it's for 4 years, we're going to have that same formula, but the exponent's going to be 4. And then the third payment's going to be 3 because we're earning interest for 3 years. The fourth payment, we're earning interest for 2 years, so the exponent is 2. And then the fifth payment, we earn it for 1 year. And the exponent is 1, and then of course the sixth payment we don't earn any interest because we put it in when we take it out. That's the confusing part. And so if we added up all of those interests together, all those payments and the interest they make, we would have the total amount in our account at the very end. Okay? This is the formula for finding future value, where R represents the payment amount, S is the future value, and so the future value equals the payment amount, R, times the quantity of 1 plus I. Now, I is the interest per period, not the interest per year. So this is compounded. This will be the same because it's compounded annually. So it's compounded once a year. So you divide the annual interest rate by the number of times compounded. If this was compounded monthly, then it would be 8 over 12. Okay? Raised to the n power. N is the number of payments. In this example, we're making 6 payments, 1 payment a year for 6 years. So the n is the number of payments, minus 1 all over the quantity of the interest per period. I'm showing you this, but you do not need to use this because, of course, we have the TVM solver. Okay, this is in your calculator, under apps, under finance, under TVM solver. Remember, n is the number of periods, and this is the number of years, times the number of compounds. So we have 6 years compounded once per year. The interest rate is the annual interest rate, again, divided by the number of compounds per year. Again, we have 1 here. Our present value is 0 because we start with 0 money in this account. Our payment is $1,500. Our future value is what we want to find, so we skip this for now. We leave the payments per year and the compounds per year as 1 because we're using the other part. And it's very important, now you see at the bottom, what this end and beginning is about. An ordinary annuity is made at the end of each period. And you can see it right in the problem. $1,500 is deposited at the end of each year. So that's one of the clues that you're going to have to be mindful of when you're doing these problems, is finding out whether it's at the end or the beginning by looking at the wording. Again, the end indicates it's an ordinary annuity. This is very important. You're going to have the wrong answer if you do that differently. Go back to the future value field. Put your cursor there, hit alpha, enter. And for this problem, you should get $11,003.89. So go ahead and try that problem. Make sure you can get the right answer. Make sure you understand each of those fields and what we entered and why. Let's look at another example. A rookie player in the NFL just signed his first 7-year contract. To prepare for his future, he deposits $150,000 at the end of each year for 7 years in an account paying 4.1% compounded annually. How much will he have on deposits after 7 years? So what are we looking for? We're looking for the future value again. How much will he have on deposit, which just means in his account, after 7 years? That's in the future. All right, so what is our N? The number of years times the number of compounds per year. So this is going to be simply 7 times 1. What is our interest percent? It's our annual interest divided by the number of compounds per year, 4.1 divided by 1. Again, we're starting with $0. We're putting in $150,000 each time, and we're trying to find the future value. If you plug this in and make sure you have end at the bottom sign, then you should get 1,188,000, etc. that you can see there. Now, unfortunately, those of us who are college professors don't get to put $150,000 away into our retirement account every month or every year. We deposit a little bit after every paycheck. So let's look at example 3. Allison, a college professor, contributed $950 a month to the CREF stock fund, an investment vehicle available to many college and university employees. For the past 10 years, this fund has returned 4.25% compounded monthly. Okay, how much did Allison earn over the course of the last 10 years? So again, now the number of years is 10 times the compounds per year, which is monthly. So our N is going to be 10 times 12. Our interest rate is going to be 4.25 divided by the number of compounds per year, so 4.25 divided by 12. Our present value is 0 because she just started the account. She makes a payment of $950 a month. We're trying to find the future value. Oops, I'm sorry, I moved through that a little bit fast, but there's the value there, $141,746.90 if you plugged all those in. If you need to, obviously you can hit rewind and pause to see what I entered in there. I thought there was going to be something else popping up. This guy up here, to make sure that you have end highlighted or underlined that you're using the ordinary annuity. Now this is a good example of a problem that gets more complicated. Part B, as of April 14, 2013, the year-to-date return was 9.38% compounded monthly. If this rate were to continue and Allison continues to contribute $950 a month, how much would the account be worth at the end of the next 15 years? Well, she's still putting in $950 a month, but the interest rate has more than doubled, which is quite nice. And it's still a monthly interest rate. So now we're going to have 15 years times 12, interest rate over 12 because it's compounded monthly, 12 times a year. The payment's $950, the future value. And we get $372,068.65. Okay, well, that kind of makes sense, right? Because in 10 years, we got $141,000 and we've doubled now the interest rate. And we've also increased the number of years. But wait, there's something wrong here. We forgot something. What did we forget? This is just what she's going to make in the last 15 years. We forget that she had 10 years before in this account where this money was. So this money is going to continue to earn interest at this new interest rate. So we can calculate that the way we've been doing in the previous chapters. So, but instead of starting with 0 as the present value in this problem, we're going to start with a lump sum of $141,746.90. Our interest rate's the same, our N is the same, the number of periods. There is no payment here because we calculated it there. And then, of course, we're looking for the future value that we would earn off of this value as well. And we get $575,691. If we add those two amounts together, we're going to get close to $1 million. Okay? So this is one of those things I'm talking about, how these problems can be tricky. We calculated what she would earn over the next 15 years from her payments, but we forgot that she already had a lump sum in that account. Now, the nice thing about the TVM solver is you don't necessarily have to do it this way. It makes good intuitive sense that since we were now calculating how much she would have at the end of 15 years, this is all right, but what was in the account at that beginning of that? The $141,000. So we could do this entire calculation at one time by putting in the balance that she had already in the account when the interest rate changed. You can do it either way, but if we had put this present value in when we changed over to a new interest rate, it would have given us this top dollar amount. So it's pretty sophisticated. A sinking fund is a fund set up to receive periodic payments. Corporations and municipalities use sinking funds to repay bond issues, to retire preferred stock, to provide for replacement of fixed asset, and for other purposes. If the payments are equal and are made at the end of regular periods, they form an ordinary annuity. This is a very common thing. So when there's a bond election to build a new school, the school has to put aside money to pay those bonds off. They're essentially getting loaned some money to pay, to build their schools, but they have to pay that back to the investors, to where the bonds come from. Okay? So, banks and financial people are very smart about financial money. They don't want us to be, but they are. And they don't want someone to not be able to pay back their debt. And so they require this sinking fund to cover obligations. So for perhaps you're starting a new factory, and the bank's going to give you a loan. Well, when the bank inspects your building, it says, your HVAC system is already 15 years old. You're going to have to replace that within the next 10 years. We need you to be building up money to replace that $50,000 system. And so that would be an example of a sinking fund to make sure that, that your asset stays valuable. Okay. A business sets up a sinking fund so that it'll be able to pay off bonds it has issued when they mature. If it deposits $12,000 at the end of each quarter in an account that earns 5.2% interest, compounded quarterly, how much will be in the sinking fund after 10 years? So this is still just a future value question. We can use our TVM solver. It's compounded quarterly, so now we're going to have the number of years times 4 because it's compounded quarterly. The interest rate per period is 5.2% divided by 4, compounded quarterly. Our present value is 0 because we have no money in the account yet. We're making payments of $12,000 every quarter, and we're trying to figure out the future value. Okay? Again, you see that it says at the end of each quarter, so we know it's an ordinary annuity. Let's look at example 5. A firm borrows $6 million to build a small factory. The bank requires it to set up a $200,000 sinking fund to replace the roof after 15 years, similar to the example I just mentioned. If the firm deposits earn 6% interest compounded annually, find the payment it should make at the end of each year into the sinking fund. So now we're looking for the payment. Again, our TVM solver does this, right? We're going to be looking for the payment. We know what our N is. Our N is how many years? 15, and it's compounded annually, so it's just 15 times 1. Our interest rate is 6% divided by 1 because it's compounded once a year. Our present value, we have no money in there, it's 0. We want to figure out our payment, so that's where our question mark is basically. And our future value is the money we need to have in that account at the end. At the end of 15 years, we need to have $200,000. So that's what we're going to plug into the future value. We're trying to save that money to replace the roof. Again, this is very simple with your TVM solver. Move your cursor to payment, alpha enter, and you can see the amount there. Let's look at another example. As an incentive for a valued employee to remain on the job, a company plans to offer her a $100,000 bonus, payable when she retires in 20 years. If the company deposits $200 a month in a sinking fund, what interest rate must it earn with monthly compounding to guarantee that the fund will be worth $100,000? So now we're looking for interest rate. This is the one time that I prefer to change the payments per year and compounds per year at the bottom, because if you do that, then the interest rate that you see in the I field will be the answer to the problem. If you don't do that and you leave it one payment per year, one compound per year, like we've been doing in all the other problems, what you're going to get here, remember, is the interest per period, the interest rate divided by the number of compounds, okay? So if we move those compounds into the CY, PY at the bottom of your TVM solver screen, then this answer is the right answer. So let's look at it. We're going to do it both ways. So we have 20 years. It's compounded monthly, so we multiply it by 12. We don't have any money in there right now. They want to give her a $100,000 bonus at the end of working for 20 years, and they're going to pay $200 a month. They're trying to figure out what interest they need to earn to do this. And if we plug this into our calculator, that's the actual answer. But what the answer you're going to see in your calculator isn't that. Try it and see what you get. You're going to get 1/12 of this. You're going to get about 0.5%, not even a little bit, actually a little bit over 0.5. Okay, because this is the interest per period, which is this interest rate divided by 12. Okay, so that's why I like to fix the payments per year and compounds per year when I'm looking for an interest rate, because what will show in this field is the correct interest rate to the answer, the annual rate, if I change these payments per year and compounds per year. The formula developed previously is for ordinary annuities, annuities with payments at the end of each period. The results can be modified slightly to apply to annuities due, annuities where payments are made at the beginning of each period. Okay, so ordinary annuities are at the end. Annuities due are payments made at the beginning of a period. This is the formula for the future value of an annuity due. Notice it's the same future value of an ordinary annuity with one additional payment, and then you take out the payment. All right. How do I know that? How do I recognize it? Notice I just have to read carefully the problem. Payments of $500 are made at the beginning of each quarter for 7 years in an account paying 8% interest, compounded quarterly. Find the future value. Again, this is going to be 7 years times 4 because it's compounded quarterly. The interest rate divided by 4 because it's compounded quarterly. There's nothing in there now. We're making $500 payments. And here's where it's really important that we make sure that beginning is highlighted or underlined in our calculator. Otherwise, you're not going to get this value. So you've got to read these problems carefully, and you've got to make sure if you're using the TVM solver versus the formulas that you make sure end or beginning is fixed the correct way. Jay Rexton plans to have a fixed amount from his paycheck deposited directly into an account that pays 5.5% interest compounded monthly. If he gets paid on the first day of the month and wants to accumulate $13,000 in the next 3.5 years, how much should he deposit? So what are we looking for here? Okay, he's going to deposit it every month, so this is a payment. It's not a lump sum here. Okay, how much should he deposit each month? That's the payment. We're looking for the payment. Okay, our N is 3.5 years, so that's 3.5 times 12 because it's compounded monthly. Our interest rate is 5.5 divided by 12 to get the interest rate per period. Our present value is 0. Our payment is what we're looking for, and he wants to have $13,000 at the end. Okay, we plug all this in, go to the payment field, making sure at the bottom we're still on beginning, and you should get a payment of $280.11.